Okay, so think about this. If a mathematical truth is true, does it need us to discover it to make it true?
Ooh, that's a good one. Yeah, that's a very deep philosophical question. We've been wrestling with that one for ages.
For a long time, right? It feels very platonic. And today we're going to dive deep into the work of someone who really took that question seriously.
A mind that changed the landscape of how we think about math. We're talking Kurt Gödel, the titan of 20th century logic. His work, his theorems, they're not just abstract mathematical puzzles. They have huge philosophical implications.
Absolutely. And for our listeners who are coming from a philosophy background, we're going to explore Gödel's work through that lens. We're not going to get lost in the technical weeds. This is about the big picture, the truly mind-bending philosophical insights that Gödel's work reveals.
Exactly. We'll be looking at his famous incompleteness theorems, his work on the continuum hypothesis, and his defense of mathematical Platonism. Each one of these is a deep dive in itself, full of philosophical twists and turns.
So in this deep dive, our mission is to get to the heart of Gödel's ideas and understand what they mean for someone like you, a philosopher wrestling with the big questions. So to get us started, tell us a bit about Gödel himself. Where did this intellectual journey begin?
Well, Gödel's life was truly fascinating. He was born in 1906, and believe it or not, he was initially interested in physics.
Oh, wow. Interesting. So his later work on relativity wasn't completely out of the blue then.
Right, exactly. But alongside physics, even as a young student at the University of Vienna, he was already deeply immersed in philosophy. He was attending lectures, engaging in these really intense philosophical discussions.
Those Vienna years in the 1920s were pretty significant, right? Especially his time with the Vienna Circle.
Oh, absolutely pivotal. That was the group with Mort Schlick and those who became the logical positivists. But here's the thing, and it's crucial for understanding Gödel.
Yeah,
He wasn't a logical positivist himself.
right.
He was his own thinker. But the energy of that group, their relentless focus on the foundations of knowledge, that definitely had a huge impact on him. It made him question the very nature of logic and how much formal systems can truly capture.
Yeah.
And later on, he really dug deep into philosophers like Leibniz, Kant, and Husserl.
Wow, some heavy hitters there.
Yeah.
So these philosophical influences really shaped his approach to mathematics and logic.
They were intertwined from the beginning. You can't separate them.
Okay, so let's talk about one of his early triumphs, the completeness theorem. This was a big deal. What philosophical problem was he grappling with there?
The completeness theorem was his doctoral dissertation, and it tackled a question that had been posed by these two big names in logic, David Hilbert and Wilhelm Ackermann.
Okay.
The question was this: can every logically valid first-order formula, a statement that's true in every possible interpretation, can it actually be proven using a formal system of axioms and rules? In other words, can our logical systems capture all the truths that are out there?
Wow, that's a fundamental question. It's about the very power of logic itself. So how did Gödel even approach this? What was his strategy?
Well, unlike others before him, Gödel started by really nailing down the definitions. He wanted absolute clarity on what it meant for a statement to be valid, to be satisfiable, to be refutable. And this emphasis on clear, precise definitions, that's a very philosophical move right there.
Right, it's about getting the foundation solid.
Exactly. And then he did something really clever. He showed that if the completeness theorem holds for formulas of a certain complexity, then it must also hold for even more complex formulas. So he basically broke down the problem into smaller, more manageable pieces.
That's a smart way to tackle it, and this led to some remarkable insights.
Oh, absolutely. So for those simpler formulas, he had to show that every valid one is actually provable within the formal system. And that meant finding a way to connect this very formal idea of provability to the more intuitive notion of truth, what a statement actually means.
It's like bridging the gap between the symbols and the meaning behind them.
Exactly. He had to find a way to show that if something is true in every possible interpretation, then it must also be provable using the rules of our system.
A tall order, it sounds like. How did he even do that?
Okay, imagine this for a second. Imagine a philosophical statement like, for every concept, there exists an instance of it.
Okay, I'm following so far.
Gödel, in a way, was looking at increasingly larger but still finite sets of concepts. He was saying, okay, if that statement is true in every possible world, then it must be true for any finite set of concepts we pick. It's like testing it on these smaller, manageable pieces.
I'm seeing how this is a way to start dealing with the infinite. We start with the finite cases.
Exactly. And then he used a powerful mathematical tool, something akin to Koenig's lemma, to argue that if you can always find instances for your concepts in these finite collections, then you can essentially piece them together to create an infinite model where the original statement holds true as well.
So it's like showing that truth in the finite cases can somehow be extended to the infinite case.
Precisely. That was his genius. And this has some profound implications for how we understand the foundations of mathematics.
Absolutely. And one consequence that Gödel himself didn't initially highlight is this idea of the failure of categoricity. What does that mean for our mathematical frameworks?
So a theory is categorical if it has only one interpretation up to isomorphism. In simpler terms, it means there's only one way to understand the theory, even if you use different names for the objects. And what Gödel showed, alongside another result called the compactness theorem, is that essential theories like piano arithmetic, our theory of natural numbers, and Zermelo-Fraenkel set theory, the foundation of most modern mathematics, these theories can't be categorical.
Wait, hold on. So our theories about numbers and sets can have multiple fundamentally different interpretations? That's pretty unsettling.
It is. You can actually construct what are called non-standard models of arithmetic, where you have these infinitely large integers that behave like numbers but are beyond our usual counting numbers. And Zermelo-Fraenkel set theory, even though it talks about these vast, uncountable infinities, if it has any model at all, it must have a model that's countable. That's the famous Skolem paradox.
So the very things we think of as the most basic and solid in math, they have this inherent ambiguity to them.
Right. And this wasn't immediately obvious to everyone, even to someone like Skolem, who had worked on similar ideas. Gödel later reflected on why this might be. He thought that there was a kind of bias against semantics, the study of meaning at the time. People were more focused on the formal symbolic side of logic, and maybe that prevented them from seeing the full impact of these non-standard interpretations.
So even in this seemingly very abstract symbolic realm of logic, the question of meaning, of what these symbols actually refer to, that's crucial.
Absolutely. Gödel believed that meaning was essential for fully understanding logic. It's not just about manipulating symbols, it's about what those symbols represent.
Okay, so the completeness theorem was a huge achievement, but it also opened up these unexpected philosophical questions about the nature of mathematical truth and the foundations of math. And then came Gödel's work on the incompleteness theorems, which really shook things up.
Oh yeah, the incompleteness theorems, those were earth-shattering. They were a direct response to Hilbert's program, this grand vision of trying to put all of mathematics on a completely secure foundation.
Right, Hilbert wanted a system where we could prove everything that was true and show that it's consistent, that there are no contradictions.
Exactly. And the incompleteness theorem showed that this dream, this vision, was fundamentally impossible.
Okay, let's break this down for our philosophical audience. What does the first incompleteness theorem tell us about the limits of formal systems?
The first incompleteness theorem says that if you have a sufficiently powerful formal system, one that can handle basic arithmetic, there will always be statements, true statements about numbers, that can either be proven or disproven within that system. It's like there are these truths that are forever out of reach of our formal methods.
That's a big blow to the idea that we can capture all truth with logic. So how did Gödel, who's deeply steeped in philosophy himself, how did he arrive at this radical conclusion?
Well, he initially wanted to prove the consistency of something called classical analysis.
Right.
But he realized that this seemed to require a very precise definition of truth in arithmetic.
Okay.
And that's where he ran into a problem. He saw that if you tried to define truth fully within the formal system itself, you'd end up with contradictions, like the classic liar paradox. This statement is false.
Right. Classic paradox. It
Yeah.
creates this self-contradiction.
Exactly. So Gödel realized he had to shift his focus. He moved from this elusive idea of truth to the more concrete notion of provability.
So instead of trying to define truth directly, he focused on what can be proven within the system using its rules.
Right. Provability is something you can define very precisely. It's about following the rules of the system to manipulate symbols. It's a purely formal property.
So it's like saying, okay, we might not be able to capture the essence of truth, but we can at least talk about what we can demonstrate, what we can prove using these rules.
Exactly. And Gödel showed that even in something as basic as arithmetic, There are truths that we can grasp intuitively, but that can never be proven within the system. It's a separation of provability and truth.
That's a huge insight. So how did he show this formally? This is where the famous Gödel numbering comes in, right?
Yes, Gödel numbering is a brilliant idea. It's a way to assign a unique number to every symbol, every formula, and even every proof within the system.
Okay.
So it's like you're turning the entire language of the system into numbers.
It's almost like the system can now talk about itself using numbers as a code.
Precisely. And this self-reference is key. Using Gödel numbering, he was able to construct a sentence, let's call it G, that essentially says, I am not provable in this system.
Wow, so a statement that refers to itself and its own unprovability.
Exactly. A real mind bender. And think about it, if G were provable, then according to its own statement, it would be false, creating a contradiction.
So if the system is consistent, G can't be provable.
Right. And if the negation of G were provable, that would mean G is false, meaning it is provable, again, a contradiction. So G is true because it's not provable, but it can't be proven within the system.
It's this weird self-referential loop that breaks the system.
It shows the limits of what formal systems can do.
Mm-hmm.
And Gödel believed that this proof was even acceptable from an intuitionistic perspective, a perspective that's even stricter about what counts as a valid proof.
Interesting. So the first incompleteness theorem was a bombshell, and then he went even further with the second incompleteness theorem. What new philosophical limitations did that reveal?
Okay, the second incompleteness theorem is even more devastating for Hilbert's program. It says that if a formal system like piano arithmetic is consistent, then it can't prove its own consistency.
Whoa, that's deep. It's like the system can't guarantee its own reliability.
Right. It's like building a house and not being able to prove that it won't collapse.
Okay, so how does the second incompleteness theorem follow from the first? It feels like they're connected.
They are deeply connected. The core idea is that the reasoning we use to show that G is unprovable, that reasoning can itself be formalized within piano arithmetic. So the system can, in a way, express the idea that if G is provable, then I'm inconsistent. And that's logically equivalent to saying if I'm consistent, then G is not provable. But we know from the first incompleteness theorem that G is unprovable, so the system can't prove its own consistency without running into a contradiction.
It's like the system is trapped. It can't talk about its own consistency without getting tangled up in the unprovability of G. And the source mentions that John von Neumann, a big name in math himself, had a very strong reaction to these theorems.
Oh, yeah. Von Neumann saw right away that Gödel had basically demolished Hilbert's program. He wrote to Carnap, another big thinker, saying that there was no reason anymore to reject intuitionism, which is a whole other approach to math. He even wrote to Gödel directly, suggesting that these theorems showed a fundamental problem with how we justify classical math.
Wow, so even back then, people realized that Gödel had changed the game.
He had shifted the landscape. It was a paradigm shift.
Okay, so the incompleteness theorems show us that there are limits to what formal systems can do. But Gödel also explored this idea of speed up in proofs. What's that about?
Yeah, speed up is another fascinating aspect of his work. It shows that even for statements that are provable within a system, there might be other stronger systems where those same statements have proofs that are way shorter, dramatically shorter.
So it's not just about what's provable, but how efficiently we can prove it.
Exactly. It's like finding a shortcut, a more elegant way to demonstrate something. And Gödel thought about this in terms of hierarchies of logical systems, like layers of increasing power. Imagine you have a simple system, like basic arithmetic, and then you have a more powerful system that builds on top of it, and so on.
Okay.
Gödel showed that there are statements that might have insanely long proofs in the weaker system, but in the stronger system, the proofs become super short.
So sometimes you need to climb up to a higher level of logic to get a better view of the problem.
Exactly. It's like you get more powerful tools to work with.
Okay, so we've seen that Gödel made huge contributions to our understanding of logic and the foundations of arithmetic, but his work also extended to set theory, particularly this long-standing problem called the continuum hypothesis.
Ah, the continuum hypothesis. That's one of those problems that really gets to the heart of what infinity means.
Right, it's about the different sizes of infinity. So what was the state of this problem before Gödel came along?
Well, it was posed by Georg Cantor, the guy who really pioneered the study of infinity. And the question is this: is there a set whose size is strictly between the size of the natural numbers, countably infinite, and the size of the real numbers, uncountably infinite.
Okay, so it's about whether there's an intermediate size of infinity, something between these two?
Exactly.
Oh.
And Hilbert, remember him, he considered it so important that he made it the first problem on his famous list of 23 unsolved problems. Some mathematicians, like Thoralf Skolem, had even suggested that it might be independent of the standard axioms of set theory.
Meaning that you could neither prove it nor disprove it using those axioms.
Right, it's like it floats free, untethered to our usual assumptions. And that's exactly what Gödel set out to investigate.
And he accomplished something truly remarkable.
Oh, yeah. What Gödel did was to show that the continuum hypothesis is consistent with the Zermelo-Fraenkel ZF axioms of set theory. This was groundbreaking. He also showed the axiom of choice is consistent too.
Hold on, he didn't prove that the continuum hypothesis is true.
No, not exactly. He showed that if you assume the ZF axioms are consistent, then adding the continuum hypothesis doesn't create any contradictions. It's a relative consistency proof.
So it's like saying, okay, if our basic understanding of sets is solid, then we can add this extra assumption about the continuum hypothesis without breaking everything.
Right. It wouldn't lead to a logical inconsistency. And to do this, he had to develop a whole new toolbox of techniques, and some of them are still used today.
Okay, so how did he do it? This is where things get pretty technical.
He constructed what's called an inner model of set theory. Think of it as a kind of mini-universe of sets that satisfies all the usual axioms, but is also carefully tailored to make the continuum hypothesis true.
Okay, a mini-universe where the continuum hypothesis holds. And this mini-universe, it's called the constructible universe.
Exactly. It's denoted by the letter L. And it's built up very carefully. You don't just throw in all possible sets. You start with the empty set, and then at each stage, you only add sets that are definable using the language of set theory itself, using elements that are already in the model.
So it's a very controlled, very specific kind of universe. And he showed that in this universe, the continuum hypothesis is true.
Yes, the idea is that every real number in this constructible universe appears at some countable level of the construction. And since each level is countable, the total number of real numbers can't be bigger than the first uncountable cardinal, Lf1. So in this universe, the continuum hypothesis holds.
Wow, that's really neat. And what about the axiom of choice? How did he show that it holds in this constructible universe?
Well, for that, he showed that there's a special way to order the sets in L, a well ordering, where every subset has a least element. And this well ordering is definable within the system, meaning we could use it to systematically pick an element from each set, essentially making the choice.
It's like the well ordering gives us a rule for making choices, so the axiom of choice is satisfied. But the source says that Gödel later changed his mind about the axiom of constructibility, the idea that all sets are in this constructible universe.
Yeah, that's interesting, isn't it? Initially, he thought it might be a natural way to extend set theory. But later, he became skeptical. He realized that there weren't many natural mathematical statements that seemed to imply the axiom of constructibility, while there were plenty that seemed to contradict the continuum hypothesis.
So he started to think that maybe the real universe of sets is much bigger, much richer than this carefully constructed L.
Right. He started leaning toward the idea that the universe of sets should be as large as possible, containing as much as possible without creating contradictions.
Yeah.
He was influenced by Leibniz's ideas about the fullness of reality.
So he was looking for what he called maximality principles, rules that would make the universe of sets as expansive as possible.
Exactly. And he thought those principles might lead to a resolution of the continuum hypothesis that was different from what he found in the constructible universe.
Fascinating. Now, shifting gears a bit, Gödel also did important work in intuitionistic logic and arithmetic, even though he wasn't an intuitionist himself. What attracted him to this area?
Gödel was always fascinated by the question of what constitutes a valid proof, what kind of evidence we need to accept something as true in mathematics. Intuitionism is a different approach to math, where the focus is on constructive proofs, proofs that actually show you how to build or calculate the objects you're talking about.
It's a more concrete, less abstract way of thinking about math.
Right. And one of the things Gödel showed is that intuitionistic propositional logic, the basic logic of propositions, is not finitely valued.
Okay, what does that mean?
Well, in classical logic, you have two truth values, true and false. But some people thought, maybe we can extend this to have more truth values. Maybe there are shades of truth, or maybe there's a third option.
Right, like maybe or undetermined or something.
Exactly. But what Gödel showed is that you can't capture intuitionistic logic with any finite number of truth values. It's inherently more complex than that.
So you can't just add more truth values and get intuitionistic logic. It has a different structure altogether.
Right. He showed that there are statements that are provable in classical logic, but not in intuitionistic logic, and no finite valued logic can capture that difference.
And he also showed that classical arithmetic, the kind of arithmetic we usually use, can be interpreted within Hating arithmetic, which is the intuitionistic version of arithmetic.
Yes, he did this using the double negation interpretation. It's a way to translate every statement from classical arithmetic into a statement in Hating arithmetic, and the translation preserves provability.
So you can take a classical proof and turn it into an intuitionistic proof, but not the other way around.
Right. And this has implications for the consistency of these systems. It means that if Hating arithmetic is consistent, then classical arithmetic must also be consistent. It's a relative consistency proof.
So it's like you're grounding the consistency of one system on the consistency of another. And this result was also noticed by Gerhard Gentzen, who is another logician working around the same time, and kind of anticipated by Andrei Kolmogorov, who was a giant in probability theory.
Exactly. And the philosopher Paul Bernays made a really insightful point about this result. He said, it shows that intuitionistic logic is not just about being super strict and finitary. It's a richer system than that.
Okay. So Gödel is really exploring the subtle relationships between these different systems of logic, and he also connected intuitionistic logic to modal logic, specifically the system S4.
Yeah, that's another amazing piece of work. He found a way to translate intuitionistic logic into S4, which is a logic of necessity and possibility. In the translation, the modal operator, usually written as a box, can be interpreted as provable.
So you're taking this idea of provability and making it part of the logic itself.
Exactly. It's like saying we're not just talking about what's true, we're talking about what can be demonstrated, what can be known.
Mm.
And this connection to modal logic is super important because it led to the development of provability logic, a whole field that studies the logic of provability.
It's like he's taking these abstract philosophical concepts and giving them a precise formal representation within logic.
Right. And the second incompleteness theorem comes into play here as well. If you try to interpret that box as provable in a system like piano arithmetic, you run into trouble.
Because the system can't prove its own consistency.
Exactly. The axioms of S4 can't all be true under that interpretation because that would contradict the second incompleteness theorem.
So again, we're bumping up against the limits of formal systems.
Right. It's like a reminder that these systems, no matter how powerful they seem, have inherent boundaries.
And finally, let's talk about the dialectica interpretation. This was a late work of Gödel's, and it seems to be about connecting logic to computation.
Yeah, the dialectic interpretation is super technical, but it has deep philosophical implications. Gödel was trying to find a more concrete computational foundation for intuitionistic arithmetic. He wanted to interpret it in terms of what are called computable functionals of finite type.
Okay, that sounds very abstract. What are those?
Think of them as a hierarchy of functions. At the base level, you have natural numbers. Then you have functions that take natural numbers as input and produce natural numbers. And then you have functions that take those functions as input and produce natural numbers and so on. It's like levels of abstraction building upon each other.
Okay, so it's a way to organize functions into these levels. And Gödel used this hierarchy to interpret Hating arithmetic.
Right. He came up with his translation that takes every statement in Hating arithmetic and turns it into a statement about these computable functionals. The idea is that the translated statement says there exist these functionals that do this and that, and for all other functionals, the other condition holds.
So instead of quantifiers like for all and there exists, you have statements about these concrete functions.
Exactly. It's like you're grounding the logic in something more computational, something more concrete. And Gödel showed that if a statement is provable in Hating arithmetic, then you can find these computable functionals that satisfy the translated statement.
So it's like a way to give a computational meaning to intuitionistic proofs.
Right. And this also gives you a relative consistency proof for Hating arithmetic. If you believe that this system of computable functionals is consistent, then Hating arithmetic must also be consistent.
It's another example of Gödel connecting different areas of logic and finding these deep connections between seemingly disparate concepts. Now, beyond his technical work, Gödel also had strong philosophical views, particularly about mathematical realism and rationalism. Let's start with his realism. What did he believe about the nature of mathematical objects?
Gödel was a hardcore Platonist. He believed that mathematical objects like numbers, sets, functions, these aren't just inventions of our minds. They actually exist in some abstract realm, independent of us.
So for Gödel, math is not just a human game. It's about discovering truths that are already out there.
Exactly. He thought that mathematical statements have a definite truth value, whether we know it or not, just like statements about the physical world. He even thought the continuum hypothesis had a definite answer, even if we couldn't prove it.
That's a bold statement. And he was also against verificationism, the idea that meaning is tied to how we verify something.
Oh, yeah. He thought that went too far. He believed that mathematical statements could be meaningful and true even if we couldn't prove or disprove them.
Okay, and he even compared mathematical objects to physical objects.
Yes, that's a famous analogy of his. He argued that it's just as legitimate to assume the existence of mathematical objects as it is to assume the existence of physical objects.
That's a provocative claim. And the source mentions some debate among philosophers about how to interpret this analogy.
Yeah, some people see it as a pragmatic argument, saying that both kinds of objects are necessary for building good theories, whether it's physics or math. Others see it as more of an epistemological claim, saying that our access to both realms is equally problematic or equally unproblematic.
So there's room for different interpretations, but the core idea is that for Gödel, mathematical objects are just as real as physical objects.
Exactly. He didn't see a sharp division between the two.
Okay, now let's talk about his rationalism. The source connects this to Leibniz's philosophy. What were the key elements of Gödel's rationalism?
Gödel was heavily influenced by Leibniz. He believed that reality has this deep rational structure to it, a kind of logical order. He thought that if we could just analyze concepts clearly enough, we could solve all philosophical problems, kind of like solving mathematical equations.
That's a very ambitious view of philosophy. It's almost like he wanted to turn it into a science.
He did. He wanted to create an exact philosophy, a rigorous system of conceptual analysis that could give us definitive answers.
And the source mentions that his later conception of exact philosophy involved phenomenology, the study of consciousness and experience.
Yeah, he was really interested in Husserl's work. He thought that phenomenology could help us identify the most basic, fundamental concepts, the building blocks of our understanding.
So he saw this connection between the rigorous analysis of concepts and the exploration of our own subjective experience.
Exactly. He was always looking for ways to make philosophy more precise, more systematic. But it's worth noting that not all philosophers agree with his approach.
Right. His rationalist program has been criticized by some, but it's certainly a thought-provoking vision of what philosophy could be.
Absolutely.
Okay, so we've covered a lot of ground here. What are the key takeaways for someone coming from a philosophical background? What's the big picture?
Well, for a philosopher, Gödel's work has some huge implications. First, the incompleteness theorems show that even in math, there are limits to what we can prove. There will always be truths that are beyond the reach of any formal system. Second, his work highlights this deep connection between syntax and semantics, between the symbols we use and the meaning they carry. Third, his contributions to set theory, especially his work on the continuum hypothesis, raise fundamental questions about the foundations of math and the nature of infinity. And finally, his commitment to mathematical realism and his vision of an exact philosophy offer a challenging and thought-provoking perspective on the nature of knowledge and the power of reason.
That's a lot to chew on. What's one particular aha moment that you think would really strike a chord with a philosopher?
I think the most mind-blowing thing is realizing that even arithmetic, something we think of as so basic and certain, has these inherent limitations. Gödel showed that there are true statements about numbers that we can never prove within our usual system of arithmetic. That's a profound insight into the limits of formalization.
Absolutely. It really shakes our confidence in the idea that we can capture all truth with logic. So as we wrap up this deep dive, what's a final question, a provocative thought that we can leave our listeners with?
Well, if even math has these unprovable truths, what does that say about other areas of knowledge, like ethics or metaphysics? Can we ever have a complete and consistent system of knowledge in those domains? And given Gödel's strong belief in the objective reality of mathematical objects, how do we explain our access to that realm? How do we know anything about these abstract entities?
Those are some big questions that we'll continue to grapple with. We encourage our listeners to explore Gödel's work further and see where it takes them. Thanks for joining us on this deep dive.